Zoom webinar like features newsletter. So as a host of events, like I know about all these cool features. Like we have some like all hands talks that we use Zoom for, and they always play music at the beginning, and I think it's coming through Zoom. And I always mean to try to check that out and play some music, but we use Zoom for. Anyways, I always play music at the beginning, and I think it's coming. Cool. All right, I think I got the thumbs up that we're live on YouTube and LinkedIn. So welcome everyone if you're joining us from YouTube or LinkedIn. We'd love to hear where you're joining us from. I am in Oakland, California. It's very nice and sunny. I feel like my instinct is to check out, peek my head out the window and see what the weather looks like, because Denny always talks about how it's gloomy in Seattle, right?
No, we tell everybody it's gloomy in Seattle, so none of you come here. Right. That's actually why we do that. So we're hiding away, in our little Pacific Northwest, and we just like say ha hi. So anyways, that's us. Yeah. So anyways, yes, I'm from Seattle, by the way, if you couldn't tell. So how are you, Stephen?
Hey guys, yeah, I'm Steven, and I am out of Toronto also. And it's also a beautiful muggy day here, but not raining, so can't complain too much.
Nice.
And I want to apologize in advance if I start, jawing on Stephen for being a Torontonian, because I'm a former Montrealer. I do want to apologize in advance to everybody on the audience here. So
nice. We have some folks. We have a couple more people in Zoom from Toronto, Adam and Zohape, I think, Sao Paulo, Calgary, and I'm checking LinkedIn too, Argentina, Bangalore, Austin, Texas, St. Louis, I think that's San Antonio, Texas, Dallas, Michigan, some more folks from Seattle. Awesome. Belgium, some more folks from India, Mumbai, Sweden. Cool. Czech Republic, Lima, Mexico. Awesome. All right, cool. Well, I think we can probably go ahead and get started. A few more folks from Toronto. Hi, Alan. Thanks for joining. I just have a few quick intro slides, so I'll get that started, and then we can get to the Tech Talk. All right.
I just realized that we call this thing Tech Talk, but it also sounds like TikTok. So I'm like, yeah, we got to be really careful about this, don't we?
Good point. That's a good reminder to make sure my pronunciation is on point. Yes, you're here for a Tech Talk, not a TikTok video. Cool. Can you all see my slides?
Looks 5x5 to me.
Awesome. Thanks, Eddie. Okay, so welcome everyone. Thanks so much for joining us. We're excited to have you. This is a Tech Talk. We have Stephen here with us from Badal.io, and he's going to be giving a talk on serverless CDC on GCP using DataStream and Delta Lake. So quick few housekeeping notes. The session is recorded. We are running it through Zoom. So hello, if you're joining us from Zoom, and we are live streaming it to the Delta Lake YouTube and the LinkedIn too. So if you're joining us in any of those spaces, there's a chat. We'd love for you to chime in, ask your questions, and we'll collect them as we go, and we'll have plenty of time for questions at the end and throughout the presentation if there's relevant points that we can address. And then the recording will be available immediately after on the YouTube link. So we have Carly here with us and Rachel, and we'll make sure we put the recording link into all of the spaces so you can have it if you'd like to reference it at a later date. And we'll also update the copy there with any relevant links that pop up throughout the presentation. So check that out there. And then I'd also like to just point you to the Delta Lake chapter page. So it's hosted on the Linux Foundation. So I'd love for you to join that page there. That's where you'll be notified of upcoming Delta Lake sessions and get all of our awesome content. We also do every twice a month, a community office hour session with Vinny and team. And so we'd love for you to join those sessions as well. And then of course, subscribe to the Delta Lake YouTube channel. And I just wanted to point out quickly that Databricks has the upcoming summit, the Data and AI Summit. Really exciting this year. It's going to be hybrid, so in person and virtual if you'd like to attend virtually. So that's going to be the end of June, so June 27th through 30th. And there's lots of awesome sessions. There's some training sessions at the beginning, lots of amazing, technical deep dives and different conference sessions. We're going to have a developer lounge and some cool spaces that you can hang out and meet different people in the community and Delta Lake contributors and lots of awesome stuff. So I'd encourage you to register and join us there. Our whole DevRel team will be there. And also, of course, most importantly, tons of awesome sessions on Delta Lake. And I think also too, Denny is doing a live podcast series with Brooke Wenig too. That should be really awesome. So lots of cool stuff. All right, so with that, I'll pass it over to my co-host, Denny, to kick things off.
Perfect. Hey, thanks very much, Karen. By the way, as a quick call out, do try to register for Data and AI Summit soon. There's both the virtual component as well as the in-person. The in-person, we're actually starting to run out of tickets. So do register sooner than later, okay? So now that I've done that little tidbit, without further ado, let's go right to Stephen. I think he's the person that you're actually here to go listen to. So Stephen, take it away. As people know, if you have questions in Zoom, put in the Q&A, YouTube, ask us questions there. LinkedIn, also ask us questions there. I'll do my best to answer those questions off the side. And meanwhile, yeah, Stephen, it's your show, my friend.
Thank you, Denny. Just give me one moment. I'm just sharing my screen. Okay. Can everyone see that?
Yep, looks good.
Awesome. Okay. All right. So first of all, thanks everyone for joining today. I really appreciate your time and attention. I know it's early on the West Coast, so appreciate anyone tuning in from there. Also, just thank you very much to Databricks for having me today. So for the talk today, we're going to be speaking about how to build a data pipeline, starting from a SQL database to a Delta Lake Lakehouse, all on Google Cloud. So as part of the talk, I'll give introductions on a few topics, including CDC, DataStream, Delta Lake, and also a new Spark connector that we've developed for connecting DataStream and Delta Lake. Before starting, I'll just give a brief introduction to myself and the people involved with this project and presentation. So like I said, I'm Stephen. It's really nice to meet you all. I'm a data engineer at a company called Bottle.io. And I also want to give a shout out to Eugene Nitsky, who's also with Bottle. He helped build the Spark connector, which I'll talk a bit more about later. Binu Matthew, who's with Databricks, and he helped us with testing the connector. And I'll see also Itai Margolin, who's a product manager of DataStream at Google. So I also want to give a quick intro to our company, Bottle. We are a GCP consulting boutique out of Toronto, Canada. And we work with clients in quite a few industries, primarily the major Canadian banks, but we're also working in ad tech, telecom, gaming, real estate, energy, and retail. We are partners with Google, where we help companies in both their cloud migration journeys with a focus on establishing network security and governance principles, but also migrating and modernizing their data products. We're doing our best to open source everything we can to help expand the GCP ecosystem. For example, we've started a project called GCP Airflow Foundations for providing an opinionated framework for executing common GCP tasks using Airflow. We are hiring in many different positions, although if you go to our careers page, it's a bit outdated, so please feel free to reach out. Okay, so gave a brief intro earlier, but let me go over the agenda in a bit more detail. First, I'm going to go through the reason for actually wanting to build the pipeline that we're talking about, and I'll also go through the high-level architecture. Next, I'll go through detail about what is CDC. I'll give a walkthrough of Google DataStream, which is a relatively new tool for replicating SQL databases using CDC. I won't spend too much time on it because there's so many great talks already on it, but I'll give a brief intro on Delta Lake and the specific aspects which are most relevant to this topic. Next, I'll go through the Spark connector we've developed. Specifically, I'll talk about the design, how to use it, key considerations, and how to tune it to your workloads. Lastly, I'll provide a short demo on running our Spark connector and a bit of exploration into the imported data from our pipeline. Okay, so getting started. So why do we want to bring data into our modern Delta Lake lakehouse? Modern clearly being a very overloaded term. So what do we mean by this? The first point I want to emphasize is that all the technology components of our pipeline and our lakehouse are built to scale horizontally, which tends to be the approach best suited for actually storing and processing very large volumes of data. Looking at our image, and please forgive me if some of the analogies don't make perfect sense, the houses, or in the case of Delta Lake, services operating on top of your data, i.e. the water, are designed to gracefully handle changes of volume, or in the case of the image, higher sea levels, thanks to the rafts they sit on. This is not really the case for traditional SQL databases, which may provide some solutions for this, like database replication and sharding, but are much more difficult to implement and maintain. And you'll have to be a bit imaginative with this Spark analogy, but you can imagine the sailboat as a fleet of high-speed motorboats capable of supporting and constructing the houses on the lake. And continuing on the topic of the lakehouse and what makes it a good one. And also, I'm sorry again about the quality of this illustration. Without data, the services of the lakehouse provide no value. So identifying our data sources and planning for their ingestion is a foundational requirement. One such source, as I mentioned, are SQL, possibly on-premise databases, which you can imagine to be the house in the top right of the image, up by a small spring in the mountains. At the time, the house or chalet seemed like a great investment, but now global warming has hypothetically gotten so bad that you can't ski or snowboard. It's become unused and decrepit and is stressing out everyone involved with it. Still, the spring at the top has some very important data, and we need a way of getting it into our Delta Lake. And this is where DataStream and Spark come into play. In addition, we likely have other sources of data, which require other periodic or maybe streaming ingestion strategies, like the plant life of our lake, or possibly one-time data loads, like the wood holding up the house. Lastly, what is a good lake house if not to support life and social activity? If nobody is leveraging the data and services of the lake house, we don't have a healthy ecosystem. That's supposed to be the Nemo and dancing person in the picture. So up until this point, I've been talking in terms of chalets, lakes, imaginary magical boat fleets, and Nemos, and I'll stop with the shaky metaphors and get more concrete. So this is how the data pipeline actually works. So starting from the left side, we have DataStream. It's a GCP service which provides serverless data ingestion from sources like MySQL and Oracle. DataStream supports two processing modes. One is an initial backfill, and second is a streaming CDC mode. DataStream exports data as JSON or Avro files into GCS, which is Google's distributed blob storage. In the future, Google PubSub will also be a supported sink. The next part of the pipeline is a Spark connector, which our team has developed. It uses structured streaming to move DataStream's GCS output into Delta Lake. The connector can be run using a Databricks cluster, which is backed by Google Kubernetes Engine as the execution backend, or Dataproc, which is Google's hosted Spark runner. Okay, so what are some, as an additional benefit to standing up this pipeline, it's not tied to Delta Lake specifically, but it also enables us to do other real-time subscriptions to the CDC event stream. On this category, there's endless use cases, but one example that I've worked on specifically is fraud detection. So we could process these events in real time using Spark in order to write fraud features into a backend like Bigtable. Bigtable being Google's hosted NoSQL database, which is more appropriate for systems requiring fast key-based lookups. Then a containerized app could be deployed onto GKE, integrated with Bigtable, and make transaction time fraud decisions. And a specific example of this could be building sign-up counts for email, IP, device, or postal code, which is Canada's zip code for our American audience, and building thresholds on top of these counts during a sign-up flow. This is a simple but effective technique for stopping promotion abuse. Okay, moving on. So I've mentioned the term change CDC quite a bit, and it stands for change data capture. So I'll provide a brief introduction to this also. CDC is a design pattern which records every incremental change made to a database system. For some relational databases, these CDC events are usually captured on the server in an ordered log, which is often referred to as the bin log. This log is leveraged for other database operations like replication, where the bin log is replayed into a new target to mirror the database. It's additionally used for things like point-in-time recovery, since you can use it to rewind and fast-forward the database state. Similarly, CDC exporters like DataStream leverage the same log and make its contents available in a more consumable way. Some examples of this include exports to distributed queues like PubSub and Kafka, or distributed file systems like GCS. So in general, CDC tools do the following. They export data in common formats like JSON, Avro, or Parquet. They append additional metadata to the raw data, such as event, timestamp, and operation type. These fields are generally really important for consumers of the data to be able to produce the ODS. I'll talk a little bit more about that later. And they generally include the kind of before and after values for each column of a row affected by the operation. So just to give a little bit of emphasis on how easy DataStream is to use, I've kind of done a semi demo here with some screenshots of just how you set up DataStream. So DataStream allows you to ahead of time configure kind of the sinks and sources that you have available to your streams. So like I mentioned, those are kind of MySQL or Oracle sources and Cloud SQL sinks. So once you have those set up, really all you need to do is name your stream, categorize the source and sink, and then on the right-hand side, you reference the existing profile. You do some pretty straightforward configuration for targeting the tables that you want to ingest. This can be done at either a schema or table granularity. And you can see also you can future-proof your pipeline with the future tables option. You need to provide a backfill strategy. So currently there's either an automatic or manual backfill. The difference between the two is backfill is basically the process of doing an IDL for your tables. And it's required because generally the logs that DataStream rely on aren't around forever. They have some kind of retention policy. Something like a week is pretty normal. So normally you need a way to get the data which isn't available in the log, and that's what backfill is. So the automatic backfill will just start as soon as you create the stream. And the manual mode, you'll have an option for triggering the IDL manually in the UI. So, and then the last step is simply just picking an output format for the files that DataStream writes. Once you've created your stream, they provide a user interface for keeping track of some statistics at a table granularity. So you can see how much data you've processed and also trigger the backfill, like I mentioned. You can also see a schema using the view details. They're also providing some straightforward graphs to do sanity checks on your DataStream stream. Once you've started, you'll start seeing your data landing in GCS in a kind of per table and date time partition format. Additionally, if you want to do some monitoring on your DataStream streams, it's very straightforward to set up. A kind of common practice on GCP is to use log-based metrics, which is a quick way of doing it. To do so, all you really need to do is define a filter query to target the specific logs that you're interested in. In this case, I'm simply targeting logs made by the DataStream service with severity error. Once you have that, it's easy to add an alert on top of that. In this case, I'm just triggering an alert if there's any logs or any errors whatsoever. Okay. Moving on to Delta Lake. Like I mentioned, I won't spend too much time explaining Delta Lake because I'm probably not the best person to do it. And also there's just an abundance of available content on Delta Lake. But here's a quick executive summary. Also, I just want to say that I'd really recommend to check out other talks on Delta Lake because they're really good for not just understanding Delta Lake, but also common problems in data engineering. So Delta Lake is an open source framework for enabling a lakehouse architecture, which is an evolution of the data lake architecture with better support for ML and certain analytics use cases, amongst other things. Delta Lake is backed by Parquet files, and in this case, in the case of GCP, those files live on Google Cloud Storage. It also has many great features such as ACID transaction support, time travel, auditing, a deep Spark integration, Scala, Java, Python, DML for insert, delete, update, and merge, and much, much more. Okay, so moving on to our Spark connector. So we've recently collaborated with Databricks to open source a Spark-based implementation for integrating DataStream and Delta Lake. The connector utilizes Spark structured streaming to bring your CDC data into Delta Lake. Using structured streaming, you get benefits such as checkpointing, which is the persistent tracking of what's been processed and unprocessed in GCS. You get the regular horizontally scalable data processing of Spark, and you also get additional debugging support with Spark UI. The connector currently supports Oracle and MySQL data, which obviously has to be exported using DataStream, and it can be run either as a notebook or a standalone Spark app. Tables are configured simply by pointing to the same bucket that DataStream is writing to. So running the connector as a notebook is pretty straightforward. You need to compile FATJAR using SBT. And then we've also created an example notebook that you can use as a template for running the connector. The cluster that you're running your notebook on will need the FATJAR that we just compiled. And once you've imported the notebook, you'll need to replace a few variables corresponding to your specific environment, which I'll give a bit more of a walkthrough on after. Running via Spark Submit is somewhat similar. You need to compile FATJAR again. You'll need to make that jar available in your Spark Submit command. And you'll also need to kind of create a configuration file. We use a library called TypeSafe, and it requires a kind of HOCON format configuration file. So you can see an example of that in the not just the project, but also in this slide here. Okay, so the connector itself, it generates 2 Delta tables per source table that you're ingesting using DataStream. One of the tables is an optional one, and we call it the log table, but it's also often referred to as the HDS. So the HDS is a table which contains every single incremental change made to that table. So it doesn't enforce any primary key constraints. It doesn't delete data. It just has everything. And it'll have access to every change made since DataStream has started running, because any of the data that came from the kind of IDL portion of DataStream, we have no clue how the state of a given row got to where it is because the log is gone for it. The second table that it generates, we call it the merge table, but sometimes it's also referred to as the target table or ODS. And this contains the actual current state of the table. So in most scenarios for the users, this is the table that they'll actually be working against. Especially if you're doing analytics or machine learning, you're most likely concerned with the current state of things. So like I said, in this table, primary key constraints are enforced and deleted data is removed. And the ODS is maintained using a merge query. So this query is something that is run on every micro batch of data in the structured streaming app, and it's run on a per table basis. So per table, per micro batch, we have a merge query that gets run. That merge query is relying heavily on the metadata that's appended by DataStream, such as what are the primary keys for this row, when was this change applied, and what sort of operation was it. So the merge query itself, this obviously isn't exactly what the code is in the project since it's using a data frames API, but the kind of spirit of the code works something like this. There's a first stage, which is kind of for each primary key in a micro batch of changes, what is the most recent change for that key? So that's what this is doing, using a kind of common rank over partition for per primary key where row number equals 1. And then the second part of that is actually merging those changes into our ODS. So again, it's done on a per primary key basis. And we have basically 3 scenarios that we're capturing. One is for deletes, one is for updates, and one is for inserts. For the delete use case, we want to see if the change that we're looking at was applied after the current timestamp of the row that we're affecting. If this change is after it, then we just delete it from the ODS. The next case is the update scenario, which again, we need to check if the change is applied after the current timestamp of the ODS's version of that row. If so, then we replace the column values of that row with the updated values. And then the last scenario is for insertions, where basically we don't need to even look at the timestamp. If there's no row for that in the ODS, then we just insert it with the current recent change. Okay, so also
sorry, just Stephen, just to provide some context, I think we got some questions here about what an ODS is versus what an HDS is. So if we can just switch back to the previous slide, just to provide some context.
Oh, for sure. Give me 1 second.
Yeah, exactly. Yeah, perfect. So just as a reminder, actually, do you want to answer or do you want me to answer? Sorry, I just realized.
Either way is fine. Maybe it might be nice to cut my monotoneness with a different voice for a bit.
No, not at all. Not at all. Okay, so HDS, i.e. the log table, is your historical data store. So basically, in data warehousing terms, it's often known as the history table as well, if you're talking about like from that context. But basically, because we're talking about tables, it's the history table data source. And while the merge table is the operational one. And so that's the quick context behind those. And so whenever you're thinking about change data capture, it's often in that form of what's the current snapshot or the operations, and also what's the log or the history that goes with it. And so that's why the terminology there. Anything else that I might have missed, Stephen, or should be added?
No, that sounds great. Makes sense. Yep.
Cool. And actually, we have a great question from, in this case, from Zoom, which is from Hemant. It's probably an abbreviation of a couple names, so my apologies. What happens if there's more than one change record in the same micro batch? So why don't you go for it?
Yeah, so it's kind of taking care of this part. Like before we actually apply the merge into the ODS, we have a step to kind of figure out what is the most recent change per primary key within that micro batch of changes. So that's kind of like the spirit of what this query is. Like because we're ordering by timestamp and some other parameters there, but mostly it's going to be by timestamp. So whichever change has the most recent timestamp within that micro batch will be the entry which has that row number equals 1 there in the query. So that's how we pick the most recent change between that. Yeah. Hopefully that answers your question.
It does. And it's Mon. Hey, Mon. Sorry, old friend. So hey, but okay, let's go right back to it. My apologies for this little detour, but I figured it would be helpful for folks listening in to get that context. So back to you, Stephen.
Okay. Thanks, Danny. Cool. So continuing on, the next topic I wanted to cover is schema evolution, which if you're familiar with schema evolution in Delta Lake, it's very similar because we basically provide the same options that Delta Lake provides. at the moment, it's applied globally to all tables being ingested in the connector. So if you're choosing the merge schema, then that's the strategy used for every single table in a given instance of the connector. And yeah, like I mentioned, merge schema is one of the options. The other one is overwrite schema. I'd highly like to recommend merge schema. And basically what merge schema is it's a schema evolution strategy, which allows for some categories of changes. And these changes are the ones that are generally considered to be acceptable and won't break things upstream or downstream. So the type of changes it allows are like things like add column and also some types of upcasting. So yeah, for example, byte into short. Generally, following like a practice like this across your whole data pipeline is going to lead to just a better overall data practice, I would say. The other option is overwrite schema. And basically, whenever a change is detected, it'll just replace the old schema with the new one. So in this way, this application will never break, which might be good, but probably all the apps that rely on that data could break if they're relying on any column which had a breaking change. So in my opinion, I would not use this option most of the time because personally, I find the mess that it creates. I mean, no matter what, there's a mess to clean up on a breaking change, but the mess is harder to clean up if you're kind of propagating it up to the applications consuming the data. Great, so the next topic that I want to cover is tuning and compaction. Right, so DataStream and Delta Lake are both using files to store their data. In the case of DataStream, you're just writing files. For Delta Lake, you're doing everything possible that you can do to a file. So achieving appropriate file size for the data is very important for the performance of your Delta tables, and also probably the biggest challenge. For DataStream, depending on the change rate of your source, you could end up with many small files. And if left unhandled, this could result in a Delta table, which is also backed by many small files. If you're running the connector on Databricks, it's gonna be a lot easier, I'll say. They have a feature called auto optimize, which can operate using a kind of target file count range or a target file size based heuristic, which it'll kind of keep your table in a good state. And this is like by far the easier way to run the connector. So, oh, actually one more thing, sorry. Also just like why is even like the file size like an important thing? Like if your Delta table is not backed by enough files, then every single change that you're gonna apply is gonna be updating or copying. Even if you're only affecting a few rows, you're gonna be having to copy over a ton of other rows which were in the same file where the change is applied. So the kind of relative rate between what you're updating and what was copied is not going to be a good balance. And yeah, on the other side of it, if you have too many files, the performance of the merge query and basically all operations are going to have too great of an overhead due to just bringing in so many files.
Yeah, actually, let me add to that. By the way,
Sure.
So just because there's also another good question on that. Oh, sorry, if you can go to the previous slide, please. There we go, perfect. Yeah, it goes back to that too many files problem. So don't forget, when you're talking about cloud object stores, the other big thing is that the listing operation is actually really, really, really slow. Okay, I cannot overemphasize that statement enough. And so because when you're dealing with too many files and it's really slow, so that's the whole point. Like you're trying to then have Spark, or for that matter, any other distributed system that I'm talking about just in general purposes here, that's trying to go ahead and read the files. So you've got so many files, you're trying to list all those files, that ends up being slowing things down massively. Okay, so that's a real quick call out. And so then July, again, I'm pretty sure it's an aggregation of a first name, last name, asked in Zoom, basically, how do you handle the Delta history log size growing too big when you're using that upsert pattern? And so just to provide some context here is that you actually have two problems, actually, not just the log files, but also the data files, okay? So the log files itself actually isn't that horrible, because what happens is that once the transaction is done, once all the data files have been written, and after the upsert is done, it basically goes ahead and just simply includes in the JSON file all of the actual file names. And so that's it. So it's not like it's not a deduplication. For the snapshot of the table at that time, it contains all of those Parquet files. Now, the problem with too many files is then that list might be too long. So that's why you want to make sure it's not that you exactly to what Stephen's talking about. You want to make sure there's tuning compaction, so that way you have the Goldilocks setup of just the right number of files, just the right size. Okay, now, and so that's why that way both the data size itself won't be too egregious, nor the log size. Now, there's also other questions about the history. In other words, if you do it too often, and so over time, you're going to need to run vacuum to basically to clear out old logs as well. And so, but that's a whole other statement, and we can probably discuss that in the Delta user Slack. So hopefully that answers most of your question. And then thank you for letting me take the pause, Stephen, so we can just answer these questions.
No worries. Yeah, great questions. So a little bit more on compaction. Obviously, it's like a really important topic when it comes to this. So we've also tried to provide some options for dealing with compaction of the data for non-Databricks use cases. So because you won't have auto-optimize or optimize available to you in a non-Databricks context. So we've provided 3 configurations that together you can hopefully tune to limit the problem. The first, and you have to kind of use them in conjunction with each other. So the first one is a merge frequency, which is how often do we read data? How often are our Spark structured streams triggered? The second, and also that means how often do we check for new files outputted by DataStream? The second one is a file read concurrency, which is how many files are we reading per trigger, per table. And the last one is microbatch partitions, which will coalesce the data in a microbatch down to this number of files. So using these together, you can slow the growth of your log table and ODS quite a bit, but you'll still probably need to schedule something to run outside of the connector. So, which will be something like a repartition of your Delta tables from time to time. Okay. Okay, and so I'm going to do a really short demo. Let me exit this. And open this. So the notebook for actually running the connectors looks something like this. It's pretty straightforward. This notebook's a little bit longer because I did a little bit of analysis afterwards. But so basically, like we have our imports getting just bringing in like the classes associated with the connector, and then we also have some types related to the configuration of the connector. Hopefully for most use cases, this is the main part, only part that you'll need to change, but the configuration hopefully is pretty straightforward. You can use these together to target the GCS bucket that DataStream's actually writing to. We have a feature here just for if you want the Delta tables created by the connector to be under a specific database, you can use this one to set that value. If you don't set it, then it'll just use the same schema or database that the source uses. Hopefully this is pretty straightforward, but just the file format that DataStream is outputting as. These are those tuning parameters that I just mentioned in the compaction setting. This is the location of your actual Delta tables. So each table will have a folder under this path, and that'll also include the Delta log for those tables. Also, the location of the structured streaming checkpoint. So if you ever want to reprocess, you can delete this one. I'm not using these right now, but also features and Databricks only configurations related to the auto compaction and auto optimize features.
Oh,
If
small favor, Steven. Sorry, could you zoom in just a little bit more so people can see?
Oh, sure. Oh, that's the wrong.
Perfect. Thank you kindly. Sorry about that.
Oh, no worries. Also, depending on if your configuration can be achieved from just modifying these variables, you may have to change this part of the notebook a little bit. These ones are actually the kind of Scala configuration classes used for configuring it. So obviously it's not quite as user-friendly since not everyone knows Scala, but we have a lot of documentation on this on our GitHub, so hopefully you can get through it. And then, yes, to actually start the connector, it's just calling the run function and passing the configuration, and that'll get your streams running. So we have one for the log table and the ODS and HTS of each of the ingested tables. And then once your tables are being ingested, you can start playing with them immediately. I'm a huge basketball fan, so I was watching one of the talks, I think it was a few weeks ago, where the Charlotte Hornets analytics guy was in to talk with Denny, and I was inspired to bring in some NBA data. So for this, I mean, he was talking about this second spectrum data, and I definitely didn't have access to that quality of data, but I ingested some free data on Kaggle, which basically just has like box score like data on a per player basis. So I've ingested that data in our pipeline already using DataStream and everything that we talked about. So what I'm trying to do is there's actually, well, another kind of aside is I'm a huge Toronto Raptors fan, and we currently have a little bit of a war going on with a certain player, Joel Embiid. So what I wanted to do is there's a little bit of feeling amongst Raptors fans that one of our former players, Marcus Gasol, is the player that turns Joel Embiid into he turns him from a Hall of Fame caliber center into a basic everyday player. So I'm hoping to be able to validate that assumption that us Raptors fans like to make about Joel Embiid. So what I'm doing here is I'm basically doing a self join between this game's details data, which, like I said, it's kind of player and also what that player did for a given game. So I'm building up a kind of joined data frame where I get the kind of player and then opponent, and also the statistical output of both the player I'm looking at and the opponent for those games. So here I'm just, I just did a quick way to kind of generate statistics for every single kind of numeric field that I'm interested in. So that's what I'm doing here. Just basically anything that we can get like an average sum or max from, I'm just building those aggregations here, or defining those aggregations. They're not actually being applied yet. So here, just building a kind of per player, per opponent type data frame. And here, just applying the aggregations that I defined ahead of time. And then, oh, sorry, let me change this. I was also going to look at the Charlotte Hornets players, since the guy who was on earlier was the Charlotte Hornets analytics guy, but I'll skip that for now. So yeah, like I said, Joel Embiid is the player that we're interested in. I have a very simplistic and very bad algorithm for what a bad performance is. Basically, if they don't score a lot, if they shoot the ball at a low percentage, and if they lose the ball a lot, that's a bad performance, with priority being on points. I was going to do something with an ML model, but I didn't have time. So here, I also have a kind of filter here for, well, like I said, this is not the best algorithm, but I'm filtering out for players who actually had a substantial role in the game that they played. The algorithm's kind of like, it doesn't tell you that the opponent and the player actually impacted each other, just the fact that they were both on the floor and they either had a good or bad game. So I'm gonna run this one again because I think it was run for LaMelo Ball, who is the Charlotte Hornets guy. And validated the assumption of crazy Raptors fans. So we could see here, based on my very simplistic algorithm, that it is true that Marc Gasol has a very odd effect on this player, Joel Embiid. You can see, just for reference, this guy averages maybe 25 points per game over his career. So he's doing half of that. 30% is a beyond horrible field goal percentage, especially for a player who is 7 feet. And also 4 turnovers is quite awful. So that's all for the demo. Well, also I just show that, like, once you have your Delta table set up, you can, if you want to interact with them using Spark SQL, you can also do the same if you don't want to use the Scala API. Cool. So I think that's basically everything.
Cool. Stephen, this is great. We did have some a couple more questions about, let's see, where was it? Oh, we did provide access to both the blog as well as the GitHub repo already. So everybody, you should have access to the blog and GitHub repos, but wondering, is there any reason why you couldn't write this in Python? Since it is written in Scala, and everybody's like going like, I want to write this sucker in Python these days.
Yeah, I don't think you can use it in Python at the moment. I'm a huge Scala guy, so that's the reason why it was done in Scala. Yeah, I love Scala. I don't know. I'm just like a fan of like strongly typed and compiled languages, and dynamically typed languages. It stresses me out, but
okay, so
yeah.
We're good. Don't worry. We're not going to get into the debate on this one. I'm a former Scala guy myself, by the way, and to Adam, who just chimed in from Zoom, is that Scala's fine, man, and we agree. Actually, you are among friends, but for the Python and SQL folks, the context is you just have to include the jar. And then you should be able to rewrite most of the stuff in Python. So I don't think there's anything against Python. Just it's more like, and don't, by the way, note the fact that what's really funny for me is that I am a Scala guy who ended up learning PySpark because of data science. And then of course, Holden Karau, she was instrumental in creating PySpark while she wrote the high performance Spark book, which was written entirely in Scala, by the way, just as a fun.
Cool.
Yeah.
Yeah, and also just to elaborate, like the hope is with the notebook that the configuration is straightforward enough that you don't need to know Scala. You just need to replace those few values with the ones for your environment. So hopefully it's still Python developer friendly.
I think so. So, and then Ravi did call out that basically he's all for Kawhi Leonard, so that's fair. I don't think we're going to debate that particular statement these days. So I think it's actually just about it. I think we're done actually with most of the questions. So my only response before we switch it back to Karen is if you do have more questions for us, please don't hesitate to ping us also in the Delta user Slack. Just go to Delta.io, and near the bottom there's a click to Slack. It's actually just go.delta.io/Delta users, in case you want to remember that, but otherwise just go to the website and just go there to go do it. But then, yeah, if you have more questions, absolutely ask us there, or basically you can go ahead and go to the GitHub repo that we've already chimed in. I'm pretty sure you can chime in all your issues there. So I think that covers for those logistics. Karen, why don't you take us home?
Thanks, Denny. Thanks so much, Stephen. That was a great talk and awesome job. And thanks everyone for joining. And so I just was grabbing the YouTube link to drop the recording link in Zoom, and then I'll drop it in the LinkedIn. So with that, thank you again. Thanks everyone for attending, and hope to see you for our next Tech Talk. Thanks. Take care.
Take care. Thank you.
Thank you.
Bye.
See you. Have a good day.